Hello everyone, I hope you are doing well. So in today's video, we are going to go through the 2022 VCE Chemistry exam, part 2 of the multiple choice questions. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah, let's smash through this video. Question 17. Which one of the following statements about sweeteners is correct? Glucose and fructose are optical isomers. Absolutely not. How? How do I look at this? If they are optical isomers, they must be basically non-superimposable. Or first, they're not even like the same structure. I mean, they're not even the same. Have a look at this. This is your glucose, alpha glucose, and this is your beta fructose. Totally different. And so if they were optical isomers, what I would do here is, if this was a mirror, and then I'll draw the mirror image of this this whole thing. So sorry, my apologies. So yep, kind of not the best drawing, but OH, like that, down OH, like that, OH, like this, down OH, and like this, CH2OH. This is the optical isomer of alpha glucose. Does this look like this? Right over here? Absolutely look. Not. Look at this oxygen. This oxygen's, totally in a different place. Absolutely not. So they are not optical isomers. So that's okay. Let's take that. Oops. Let's go. Okay. Not optical isomers. B. Glucose reacts as a monomer in the body. True. Remember, glucose is the most basic unit of a carbohydrate. So it is actually a monomer or a monosaccharide. So yeah, it reacts in the body as a monomer in the body. Yeah, it reacts, for example, cellular respiration and other kinds of very hard processes in the body. Yeah, so it does act, glucose reacts as a monomer in the body, such as cellular respiration. So we can put a tick on that. C. 2 moles of glucose has the same energy content as 1 mole of sucrose. Not true. Sucrose is a totally different, absolute molecule. Like, for example, so sucrose is a combination here. Sucrose is a combination of a glucose molecule and then basically a fructose. So, of course, 2 moles of glucose is not going to be the same energy content of 1 mole of sucrose. Absolutely not, because fructose has totally a different energy content, and glucose also has a totally different energy content. And so when you combine two of them, there's gonna totally be sucrose is overall different. And whereas if you have 2 glucoses, they're not gonna be the same. Absolutely makes sense. So yeah, they're not gonna be basically having the same energy content. So we can put a cross on that. D. Sucrose has an energy output almost 200 times the energy output of aspartame. Not true. It's actually sucrose and aspartame actually have this close to the same energy content. But the difference is aspartame is 200 times more sweeter. That's the difference. So the energy outputs are going to be the same, but aspartame is 200 times sweeter. So not 200 times the energy output. So choose B. Question 18. A student wants to investigate a galvanic cell consisting of SN4 plus ions and SN2 plus ions and Ag plus and Ag half cells. Alright, which of the following combinations of electrodes and solutions will produce an operational galvanic cell? Alright, remember, to make an operational galvanic cell, it needs to, you need to make sure it is a spontaneous reaction. So in the SN4 plus and SN2 half cells, remember both of these are ions. So you want to actually use, you don't want to use a solid SN because both of these here are ions. So you would basically use graphite. Whereas gold, you can actually, it's saying Ag solid, so you can actually use a electrode, like a gold electrode. So yep, you can use so C and D are still, gold as electrodes. That's what they've done here. So remember, if they are solutions, make sure to use an inert electrode, such as graphite, carbon, other ones I forgot. But yeah, so, Now, we need to double check. So the difference is what? So these are the same, but the difference is one has this and the other one doesn't. Let's just double check if I use my electrochemical series. All right. Let's see. So the first one is, so it has this and that, which is basically SM4 plus ions. Where is that? Here. And SM2 plus ions. So this one and this one. And also Ag plus ions and Ag solid because of the electrode. Those and those. So which one is the highest, which one's going to basically create a, so we can see that, like, remember, for it to be spontaneous, it must react like this. Like this. And yes, there is actually. Look, this is reacting with this, and hence it's going to be a spontaneous reaction. So this does actually produce a galvanic cell. Now, let's try the other case, where now you've took SN2 plus out. So anything with SN2 plus, let's take those out, and let's see what happens. All right, SN2 plus. Ah, now it's a big problem. So we got nothing to react it with. You remember, it has to be like this arrow. See, there's nothing, so it's actually not a spontaneous reaction. So basically, yeah, the other one doesn't give you a spontaneous reaction. So it's only C, so 18C. Let's choose 18C. Beautiful. Question 19. Which of the following chemical compounds contain a chiral carbon center? Remember, for a carbon to be chiral, it needs to have 4 different groups attached to it. Let's try to look at glycine. So glycine is a amino acid. So let's use our electrochemical data book. All right, go down. Glycine, which is G. There it is. This is your glycine. Absolutely not. You can see that this carbon here has 2 of the CHs, like hydrogen and hydrogen, so it has the same atom, so rubbish. B, glycerol. Glycerol, let's check glycerol. So glycerol, going up here, let's have a look at this. Okay, this one absolutely not this carbon, because it has the same atoms here. What about the middle one? Now, the middle one actually is still not, because this part here, if you look at this part and this part here, are equal. They have the same, basically, the same group are attached. So that doesn't work also. Butane 2-ol. Okay, let's actually graph that. Let's see what that looks like. How does butane 2-ol look like? So 1, 2, 3. So at 1, 2, there's going to be an OH group. 1, 2, 3. So like that. Okay, like that. Let's see. Yeah, this one actually does. So this carbon here, this is a ethyl group. This is a methyl group, OH, and a hydrogen here. So this one actually looks good. So we put a tick on that. Let's check the other one. So propane. So 1, 2, 3, and at 1 it has both chlorine, and a hydrogen. Absolutely, this is rubbish. You can see this is rubbish. This is not, and this has 2 of the chlorines. Does not work. So it is actually, choose C, 19C. Question 20. The equipment below was set up by a student. Okay, so we can see that he's put like zinc metal on this. Okay, which of the following is correct? In the beaker, the reaction between zinc and this produces voltage. Okay, let me tell you one thing. The hell no, this is not going to produce any voltage. Why is that? It's not a circuit. If they do react, it's just going to be a spontaneous reaction that's just going to release thermal energy, heat energy. It's basically chemical energy to heat energy. There's not even a voltage that's going to be produced. So straight away, anything with voltage, especially with this that has no, electrons basically flowing, is taken out in the subject. So take it out. In the beaker, chemical energy is stored in a reactant and is converted to heat energy. So chemical energy stored in a reactant is converted to heat energy. Well, let's check if they actually do react. So for reaction, let's see if they do react. So what do we have? We have zinc solid, CO2 plus, and Mn2 plus. So let's highlight them in our electrochemical series. All right, here it is. So we've got zinc solid. So zinc solid is where? All right, where am I looking at? Okay, zinc solid's here. CO2, that, and Mn2 plus. Where is Mn2 plus? There it is. So this over here, yes, these two are going to react spontaneously. So in the beginning, yes, they are. Yeah, these react spontaneously and hence are going to produce heat energy. So yeah, the chemical energy stored is going to be basically used as heat. So we can put a tick on that. Okay, in the beaker, the concentration of ions increases because zinc loses 2 electrons. Let's check. Now, so we can see that this zinc is going for oxidation, which is the loss of electrons, and it's losing 2 electrons, which is true. But it says in the beaker, the concentration of ions increases because of zinc. So, okay, we are releasing zinc ions. But the thing is, we are consuming, to make cobalt solid, we are consuming cobalt ions. So actually, they're not telling us anything about cobalt. So it could be like, we are forming zinc, but we're like taking much more cobalt. So there's like a net flow of nothing. So basically, these are cancelled out. This is being used up, whereas zinc is being produced. And in other words, yeah, is there an increase? That we don't know. So it's not very being specific, so I don't think this is correct. It needs to be much more specific, yeah. Depends, yeah. So in terms of concentration, the concentration of ions increases because of zinc. Not true. Doesn't increase because of zinc. So yeah, it has a part, but yeah, it doesn't talk about cobalt. D, in the beaker, a voltage of greater than... Okay, it talks about voltage. Take that out in the bin. Remember, this has no voltage. It's not even going to create anything. Remember, it is not any. It's not an electrolytic cell, a galvanic cell. It's not a circuit. So 20B. 21. Consider the following statements about enzymes and coenzymes. All right. Enzymes and coenzymes are not changed during a catalytic reaction. Now, yes, enzymes are not changed, but coenzymes sometimes do change. They actually can change, so that is not right. Second, all catalytic reactions require a coenzyme to proceed. Not true. Some do, but not all of them, so that's just being too much. Coenzymes can lose or gain electrons due to a catalytic reaction. True, because remember, coenzymes not just function, they go to the active site and change, shape of the active site so the substrate can, fit in, but it can also act as a, electron carrier, an atom carrier, all of these. So it does actually work. Coenzymes are inorganic molecules. Straight away, rubbish. Are organic molecules, remember that. Coenzymes can change the binding properties of an enzyme to allow the reaction to occur. Beautiful, this is what we just talked about, how coenzymes basically attach to the active site, fit it, make sure it's perfect, so the substrate can fit in perfectly and allow the reaction to occur. So only VN3, which looks like D. That looks good. Next question. Lithium-ion batteries are used in a range of electronic devices, including mobile phones. So the discharge for this type of battery is given here. Which of the following is correct about the lithium-ion batteries? So during discharge, reduction occurs at cathode. Remember, reduction, any electrolytic cell, galvanic cell, always reduction occurs at the cathode, doesn't change. So cathode. Yep, so it could be not just that. And during recharge, reduction occurs still at the cathode. So D. Be careful with that. Remember, cathode, always reduction. That's it. For both. So easy. 23. Which of the following statements about lithium-ion batteries is correct? So, during recharge, lithium CO is formed at the negative electrode. Well, let's check from this equation. So saying during recharge is formed. Rubbish. It's used up. So take this here. This is your discharge. We're talking about recharge right now. So flip it. So this is going to be CO2 plus C6 gives us CO O2 plus LiC6. You can see that when it's recharging, CO2 is being used, not formed. So rubbish. B. During discharge, so this here, Li ions move towards the positive electrode. So during discharge, it acts as a galvanic cell. And we know galvanic cells, positive ions, always flow towards the cathode, which is positive. So that is true. And remember, it's the opposite. When it becomes an electrolytic cell, the positive ions goes towards the negative electrode in electrolytic cell. So, yep, B looks good because it's, yep. Let's have a look at more. Raising the battery temperature increases the rate of reaction. True, thereby increasing the battery life. Rubbish. If you're increasing the rate of reaction, you're increasing the rate of other side reactions, which deteriorates the battery life. So absolute rubbish. D. The battery operates as an electrolytic cell during discharge and galvanic during rubbish. That's, yeah, you know that. Remember, electric cell is when it's recharging and it acts, when it's discharging, it acts as a galvanic cell. So the opposite. So 22 is actually B. So, sorry, 23 is B. Next question. A high-performance liquid chromatography (HPLC) instrument is set up with a polar mobile phase and a non-polar stationary phase. The amino acids leucine, alanine, and asparagine, I don't know how to spell that, are added to the mobile phase and they run through the HPLC. The order of the retention times from the shortest to the longest for the free amino acids is what? Alright, let's think about it. So we're using a non-polar stationary phase. So let's just draw a nice cube here. Imagine this is our stationary part and it's non-polar. So we know that non-polar molecules and non-polar stationary phase, they like to attract each other. They like to kind of bond together. So meaning that the higher the retention time, the longer the retention time, the more polar the molecule is. The more the non-polar molecule is, because remember this is non-polar, the stationary phase. So if we have a non-polar molecule, the more non-polar molecule that is, the higher the retention time, because it's more bonded towards it, so it slowly goes down because it's attracted to that actual stationary phase. And so remember, the more polar it is, it's going to straight away go down because it doesn't want to even be attracted to that non-polar. It's going to go straight away down, so the retention time is much shorter. It's quick, the time it takes, yeah. So let's write here. Okay, so basically what we said is non-polar. So it's saying from shortest to longest. So the shorter retention time is basically when it's more polar, when a molecule is more polar, and the longest is basically when it's non-polar, because non-polar means that it's very attracted to it. So which of these here is more polar and non-polar? We just gotta rank them. All right, so the first one is leucine. So let's go down, back. All right, here they are. Leucine, where are you? There it is. Leucine's here. So we can see that leucine is, all of them, by the way, have this. So just ignore that right now. So you can see that we have this very actual non-polar side of it and comparison to the polar side of it here. So, okay, that's that. So it's like more non-polar. Alanine, let's look at alanine. So alanine is here. Alanine actually has just a small non-polar side. So it's actually like, it's going to be considered more polar, by the way. Because look at the non-polar side compared to the polar side. There's much of a more polar side than the non-polar. In comparison to this here that we said, this is your non-polar side here. And this is your, This is your non-polar side and this is your polar side. And we can see that the non-polar side is much larger compared to alanine. So, and what about asparagine? So this one here, where is that? Go up here. There it is. So, no, this one over here is much more polar. Look at this. You have a non-polar side here and also a non-polar part here. So it's like in comparison to that CH, of course, but it has a very large non-polar. It's more non-polar than all of them. So the most non-polar is that asparagine, ASN we call it. So it's ASN, short name. And what's the second most polar? We said that it was alanine because it has a very short non-polar side. So alanine, so ALA. And the actual, the most non-polar is your leucine, so LEU. Beautiful. So let's put these, which one looks like that? ASN, ALA, and D. Looks like D is your answer, so 24D. 25. Consider the following statements regarding biodiesel and petrodiesel. Petrodiesel is more hygroscopic than biodiesel. Rubbish. Biodiesel is more hygroscopic. It likes to take moisture from the air. Because why? Because it has a ester group. It has this ester group that makes this, makes it slightly non-polar, and so hence, remember, it attracts water because it's it makes it more polar because water is also non-polar, so it likes to attract water because of that ester group. Biodiesel forms crystal at higher temperatures than petrodiesel. Yes, remember, biodiesel has a high clouding point. So it does actually form these crystals. So true compared to petrodiesel. So I'm going to put a tick on that. Biodiesel and petrodiesel are derived from plants and animals. True. Be careful here. Don't get confused. Now, I think a lot of students think that plants are like, biodiesel. Remember, petrodiesel is formed by the decompositions of plants and animals over millions of years. So it still derived from plants and animals, but it takes millions of years to basically decompose to make petrodiesel, which is why it's not renewable. But it is remote. Its derivation is from plants and animals, and also biodiesel. True, you can get from plants and animals also biodiesel. So there are both that. So this is true. So wait, that's true and that's true. We did forget that. The combustion of biodiesel releases less sulfur dioxide than petrodiesel. True, biodiesel is, petrodiesel is much, from like, it's taken from the ground. So basically it does have some more contaminants, petrodiesel. So it does release like, nitric oxide, sulfur, it's more contaminants compared to biodiesel. So that is correct. So put it correct, that's correct. So only, which one of the following statements are correct? So these ones. Looks like D is your answer for that one. Next question, 26. Calorimeter 1 and calorimeter 2 were each electrically calibrated. The same current, voltage, and time were used to calibrate. So basically, if you have the same current, voltage, and time, you're basically giving them the same energy. Remember, voltage times current times time is your energy. A reaction was undertaken in calorimeter 1 and calorimeter 2. The same amount and type of each reactant was used in both calorimeters. The following temperature versus time graphs were produced for the reaction in each calorimeter. So we can see that calorimeter 1 has this nice constant value here, meaning that it's very nicely insulated. So it's like 100% no energy loss. Compared to calorimeter 2, you can see that then at the end there is this heat loss. So it's not perfectly insulated, we can see in calorimeter 2. Now let's look at the questions. Which of the following statements is correct? Only calorimeter 1 can be used to calculate change in H. Rubbish. You can actually use both of them because what you can do, you can use both of them because you can actually standardize, like make sure you can use like a coherent line that follows it, and you can actually calculate that change in temperature, and you can use it to calculate your enthalpy change. Remember, realistically in life, you don't get something like calorimeter 1. That's like 100% like no energy loss, which is, of course, that's not realistic. When you do these experiments, you're going to see them like the calorimeter 2, there's going to be always energy loss. Nothing's 100% efficient. So, so of course we can calculate the change in heat using the change, calorimeter 2, not just calorimeter 1. So absolutely. Make a best line of best fit and calculate that temperature change. That's what we do. Calorimeter 2 has better insulation than calorimeter 1. Rubbish. Calorimeter 2 has even worse insulation. Like we said, there's an energy loss. It goes down after. C. The calibration factor for calorimeter 2 is higher than the calibration factor for calorimeter 1. Well, let's check that. So, we know that the calibration factor is your energy over your change in temperature. Now, we know energy is the same, like we said, because they use the same voltage, current, and time. Now, let's calculate the temperature change here. So, this one over here is 35 minus 15, which is 20 degrees Celsius. That's your temperature change. Whereas this one here is 30 minus 15, which is 15 degrees Celsius. So the calibration factor, basically, the higher the change in temperature, the lower the calibration factor. This one has a higher temperature, so it has a lower calibration factor. This one here has much of a less one, so it actually has a higher calibration factor compared to calorimeter 1. So it says calibration factor of calorimeter 2 is higher. Yes, then calibration factor, yep, that works. Beautiful, that's what we just said. D, during the calibration, the temperature increases the temperature increase of calorimeter 2 was greater. No, it's much less. This one's greater. Calorimeter 1 is greater, so that's wrong. So choose C as your answer. So 26, C. 27. Which of the following reactions has the highest atom economy in the production of an organic molecule? So let's check this. So complete combustion of propane. So let's do that. So C3H4. So we have to actually write the reaction. You react with oxygen gas, and hence it releases, of course, CO2 and H2O. So there's 3 carbons. There is 4 hydrogens, and there's, so that's 6 plus 2. So there has to be 4 oxygens. So this is our reaction. Remember, to calculate your atom economy, you need the molar masses of what you want. Your key, we want the organic molecule for our product. So this one over here, that's our organic molecule. This is an inorganic molecule. So this carbon here, so if it's 3 times, we can see, because of the 3 here. And what is its molar mass? We have, of course, your carbon, which is 12, plus 2 16 because of the 2 oxygens, divided by your total reactants, total molar mass of the reactants, which is 3 carbons, 4 hydrogens, we have 8, so 4 times 2, we have 8 times, so we have 16 of those, and we times it by 100 to make sure we get it in a percentage. So let's do that. That's going to be 3, 12, 16, 3 times 12, plus 4, plus 8 times 16, times 100, and so we get 76%, approximately. No, 79, what am I doing? 79%. 79%, this one, okay. Let's do the next one. All right. I mean, this is very long. Okay, reaction of iodine with propane is what? So it's an actual alkane. So what you need is like UV light, of course, to make this reaction occur. So what's going to happen is we know this reaction is going to basically, when you're of iodine 2, it's going to have, so it's going to release HI and the C3H7, and it's going to have 1 I in it. So this is our reaction. And so now what we want to do is we want to find, remember we want the organic molecule. So we have 3 times 12, 12 carbons. We have 7 hydrogens. And how much is iodine? What is its molar mass? We can calculate it using our formula, a data book. So we want the molar mass of iodine. Where is that? Having a twist of my head. Iodine. It is 126.9. 126.9. All right. So 126.9. So, and now we do calculate the overall total molar mass of the reactant. So 3 times 12 plus 8 plus 2 times 126.9. And make sure you times it by 100 to get in percentage also. 3 times 12 plus 7 plus 126.9. And so 3 times 12 plus 8 plus 2 times 126.9 and times it by 100. So that gives you basically like 57%. 57%. Next one. Wow. This is very long. I'm not going to lie for a question. Next question is reaction of bromine 2 and propene. So yes, this is an alkene. So this is going to result in so C3H6 reacting with bromine 2 is going to release in basically C3H6 bromine 2. This is good because this is 100% atom economy. Remember, we're going to find the molar mass of all this. So like 3 carbons, 12 plus 6, hydrogens plus 2 times your bromine, blah, blah, blah. But it's the same as this. So look, 3 times your carbons, 6 hydrogens, 2 times your bromines. This is just going to cancel out to 1, and you times by 100. That's 100% atom economy. So I'm going to choose C. I'm not even going to do D. It just takes too long. We know this is the highest because it's 100%. So makes sense. Wrote that out. Next question. 28 carbon NMR spectrum of an organic compound is shown. So how many peaks? We got 1, 2. So we got 1, 2, 3. We also have 4, 5. We have 5. Why is this so close? That's what I'm saying. Oh, but we have 5. All right. So we have to have 5 carbon environment. The organic molecule could be what? Okay, let's have a look at this here. We will have in this one, there is no symmetry. Like if you draw it, so it's C, 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 O, H. So there is no symmetry. So what's going to happen is we consider that's going to be 1, 2, 3, 4, 5. Yep, it does fit the condition. So we're going to put a tick on that. It could be this. Let's try the next one. So this one here. So we have C, C, double, so C, wait, C, 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 double C. So 1, 2, 3, 4, 5, 6. So 2, 3, 4, 5, 6, and an OH. Let's have a symmetry here. Looks like there is no symmetry here. So it's going to be 1, 2, 3, 4, 5, 6. 6 carbon environments, rubbish. Take me out. It's supposed to only have 5. Next one. This one over here, we have C, C. So we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 OH. This one, yeah, there's no symmetry, so overall 1, 2, 3, 4, 5. This one could also be that one. Damn, there's already 2. What about the last one? So we have an OH. So we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. And there's a carbon double bond here. Is there symmetry here? Let's check. Nope, not symmetry. So that's going to be 1, 2, 3, 4, 5. That's also 5. What? So it could be possibly 3 of these. Now, the way that I'll try to like get rid of most of them is basically now you have no choice. Let's use our actual data book and see which one works. Like for example, this one over here has a CH. Like you know how it has a so when you start, this one has a CH3 here. So a CH3 at the end. So let's check if there's a CH3 on our, what is the, like, what is CH3 on a carbon NMR? CH, there it is, carbon NMR, CH2. So the first one is around 8 to 25. Where's 8 to 25? 8's around here. 25 is here. There's no peak here. So it doesn't have a CH3. So A is straight away wrong. It's no way there. Now the difference here is that one has carbon, like a triple bond, and the other one has a double bond. So let's check which one it would be. So which one has a, wait, this one has a triple bond. So where is it supposed to be lying between? 75 to 95. 75, which is here, to 95, which is here. There's nothing that's lying between it. So it's not actually that triple bond. It has to be then D. So the D has a triple bond. What do you call it? A double bond. So this one, 110. So where's 110? Here, to 150. Is it? Yep, 150. This, yeah, these two lie between it. So yes, it has to be that one. So let's look at that. So 28 must be D. 29. 1 mole of methane, CH4, reacts with 1 mole of halogen, X2. X can be fluorine, fluorine, chlorine, yep, and bromine. The general equation for this reaction is given. So we have methane. Okay, reacts with this, gives us this. Okay, makes sense. Which of the following statements is true? The strength of the bonds from the weakest to the strongest is this. Okay, let's think about it. All right, we know that the more electronegative the molecule is, like for example, that bonds with C, for example, we know the most electronegative molecule is fluorine. Remember, because it's at the most right and the most top in the periodic table. Fluorine. So think about it. Imagine you have carbon here, and fluorine is so electronegative, meaning that it basically creates its, it takes all those electrons and creates this partial negative charge. I can't even draw that partial like that. This one hence creates a positive charge. Like this positive partial charge, and hence the bonding between them, because they're very strongly, there's this positive and negative, they're going to be bonded very close to each other because the strength of those. So they're going to be bonded very close to each other, and the more the bond length is shorter, the stronger it is. Now, we know fluorine, because it's more electronegative, it's going to be attracting that carbon so much more. So it has to have a stronger, it has to have a much smaller bond length, and hence stronger bond. So the strength of the bond. So high electronegativity means the stronger the bond. So fluorine has to be the strongest. Then it has to be what? I think chlorine and bromine. So was it in the electrochemical? So what was it? I think it was, so it was fluorine, which we know is the first. Where is that here? Fluorine, yep. So fluorine, then chlorine, then bromine. And so, yeah. So which of the following is from the weakest? Well, weakest is bromine, then chlorine and fluorine. Yeah, this one's good. This actually talks perfectly. This one looks good. Next one. Since hydrogen has the smallest atomic mass, the CH bond is the weakest one. Rubbish. Remember, the smaller the atomic radius, the more the stronger the bond. Absolutely rubbish. So, yep. Since hydrogen has a smaller atomic radius, the CH bond is the weakest. It's actually going to be the strongest. The more smaller the radius, the more stronger it is. See, the so chlorine to bromide bond is stronger than CDH bond because of the size of the bromine atom. So look, there's also a sequence. So the bigger the atom, this is what they say, the bigger the atom compared to a smaller, the bigger the atom, the more the actual radius is that length, the bond length is. And remember, the bigger the bond length, the more weak it is. So bromide is bigger, of course. So no, absolutely, because bromide is bigger, it's going to be weaker. The bigger the element is, for example, bromide, it's going to have a bigger radius or a bigger bond length, meaning that it's weaker. It's not stronger than CH. CH is actually small, has a much stronger because the H is much smaller. And so, yeah, absolutely rubbish. D. C to B, C. Okay, these bonds are equal in... No, absolutely not. They are not equal in strength. Be careful. Fluorine's much more electronegative than more than them, so it's the strongest. So it has to be A. Beautiful. 30. Consider the following half equations which are not in standard electropotential order. Makes sense? So these are just basically a mixed. We don't know which one's like, yeah. The following is also known. Yes, I've seen these questions so much in exams. They are so easy. Take your time with them. Don't rush them. For example, this here. So where is it? In this. Here. So iodine reacts with bromide O3. So this one over here. Where is it? This. So it reacts with it. And HBRO. So it reacts with those two, but does not react with this over here. So what does it mean? It means these two have to be larger. They have to be on top of it, more on top of the electrochemical series than this over here. Because remember, it's going to be a spontaneous reaction. Like, for example, this was already good because there's a spontaneous reaction between them. But this here must also be on top too for a spontaneous reaction. So what's going to happen? So we're going to write, so the first one, so HBRO. I'm not going to write like the electrons and stuff. It goes to half BR2. So that one's, and this one also has to be larger than this. So I'm going to say BRO3 goes to BR minus, okay? And then the iodine has to be at the bottom. So 2IO3 minus goes to iodine squared. Does this make sense? Yes, it does now. See, I2 reacts with bromide this, so you can see that it's here, and BRO3 is here. Yes, they can react. Same as with the HBRO. Oops. It's at the top here. So it's at the top here, and hence react also too. Beautiful. So a spontaneous reaction. But not with HCrO3, means this here has to be at the bottom. So HCrO4 minus goes to Cr3 plus. We're only drawing. Okay. Next thing. Bromide, so this one over here reacts with HBRO. Yep, that's good. See, this one's at the top, and this is a spontaneous. Yep, that works. But not with IO3. True, yeah, it's not going to react because that's the bottom. Beautiful, it won't react. That still meets the conditions. This is good. Platinum electrodes were used in each half cell. So this is actually the order, basically, of how it's going to be looking at it in terms of electrochemical cell. And which of the following galvanic cells will produce the highest potential difference, so the voltage. Easy, remember, the higher they are, so like for example, if you take this, the highest and the lowest, you minus them, you're going to get the highest potential voltage because the distance. So let's try to check which one's the first one. You got HBRO and BR2, so this, and HCrO3, so this over here. So yes, they are the longest. You can see that the distance is the longest, meaning that they basically, yes, produce the highest voltage. So this is good. So I'm going to put a tick on that. Let's just check the other ones. See if they, HC3, so that one, and BR3. Nope, it's much smaller than the other ones. Next one, BRO3IQ, so this one here, and IO3, still small. You can see the distance. HBO this, and IO3, still small. So the largest distance was actually A. What a beautiful ending of a question. I hope you guys enjoyed the video, this video. Please make sure to like and subscribe for more future videos like this. I hope you guys enjoyed the video and learned something through it. Please take care of yourself, guys, and have a great day. Bye-bye.